The question asked, on the axes provided, sketch a slope field for the given differential equation at the 10 points indicated. So we're going to plug in the coordinates of the x and y point and plug it into the differential equation to find the slope of the line at that point. So starting off 2, 1, when we plug that into the point, we get -2 plus 1 over 1, which gives us -1. So we're going to draw a line with the slope of -1 at that point. Going to -2, 1, when we put that into the differential equation, we get -2 plus 1 over -1. So we're going to draw a line with the slope of 1 at the point. Next, we are going to plug in the point -1, 1, and when we plug that into the differential equation, we get -1 plus 1 over 1, which equals 0. So we're going to draw a horizontal line at that point. And the next point is -1, -1, and when we plug that in, we get -1 plus 1 over -1, and we get 0. So we're going to draw another horizontal line at that point. And for the next points, we get a slope of 1 for the point 0, 1. For 0, -1, we get -1. For 1, 1, we get 2, and so forth for the rest of the points. So the next question asks, let y equal f of x be the particular solution to the given differential equation such that the line y equals -3 is tangent to the graph of x. Find the x coordinate of the point of tangency and determine whether f has a local max, local min, or neither at this point. Justify your answer. So we're going to start off by using the given differential equation, and we're going to set this equal to 0 because we know that the point y equals -3 is a horizontal line, so it's going to have a slope of 0, and we're also going to plug in -3 into the differential equation. So doing that gives us x plus 1 equals 0, and then solving for x gives us -1. So now we know the x coordinate of the point that intersects or is tangent to the line y equals -3. So now we have the point -1, -3, and now we need to determine if it is a local max, local min, or neither at this point. And we can do this by taking the derivative of the differential equation, which gives us y minus x plus 1 times dy dx over y squared. And plugging the point -1, -3 gives us -3 plus -1 plus 1 times dy dx over -3 squared, and that gives us -3 minus 0 times dy dx over -3 squared. And to simplify that gives us -3 over 9, which equals -1 over 3, and this is less than 0, so we know that it's a local maximum at this point because it's concave down at x equals -1. The next question asks, let y equal f of x be the particular solution to the given differential equation with the initial condition f of 1 equals -3. Find y equals f of x. Use the solution to f of x to determine f of 0.5. Solve for y. So again, we're going to start off with the given differential equation, and we're going to cross multiply, and that gives us x plus 1 dx equals y dy, and we're going to integrate both sides of this, which gives us the integral of x plus 1 dx equals the integral of y dy, and integrating that gives us 1 half x squared plus x plus c equals 1 over 2 y squared. And we know to find c, the value of the constant, we're going to plug in the point 1, 3 because that's the given point for us. So simplifying that gives us 1 half plus 1 plus c equals 9 halves, and that equals 3 halves plus c equals 9 halves, and therefore c equals 3. So we can plug that back into our equation for the line, and that gives us 1 half x squared plus x plus c plus 3 equals 1 half y squared. And now we need to solve for y, so we're going to multiply both sides by 2. That gives us x squared plus 2 plus 6 equals y squared. And to continue solving for y, we need to take the square root of both sides. And because we know that the point f of 1 equals negative 3, when you take the square root of both sides, or of the left side, it has to be negative, because that's how we could get a negative y value, as shown by f of 1 equals negative 3. So doing that, we get f of x equals the negative square root of x squared plus 2x plus 6, and that is our solution to the differential equation. And now we can use this equation to determine the value of 0.5, and plugging in 0.5 into the equation gives us the negative square root of 1 half squared plus 2 times 1 half plus 6. And simplifying that gives us f of 0.5 equals the negative square root of 1/4 plus 1 plus 6. And simplifying that gives us negative 2.692582404. The next question asks, let f be the function that satisfies the given differential equation. Write an equation for the tangent line to the curve through the point f of 1 equals negative 3. Then use your tangent line equation to estimate the value of f of 0.5. So we're going to start off again by using the given differential equation, and we're going to find the slope at the point at 1, negative 3 by plugging in 1 and negative 3 as the x and y values for the differential equation, and then that gives us 1 plus 1 over negative 3, which equals negative 2/3. And because now we know the slope at the point f of 1 equals negative 3 is negative 2/3, we can write the equation, which comes out to y plus 3 equals negative 2/3 times x minus 1. And now we can use this tangent line, to estimate the value of 1 half, which is found to be negative 2.667. Part E says, compare your result of f of 1 half found in part D to the actual value of f of 1 half found in part C. Was your estimate from part D an underestimate or an overestimate? Justify your answer using calculus. So we're going to use the given differential equation again, and we're going to take the derivative of it, which we found earlier, and we're going to plug in the original differential equation into where it says dy over dx. And when we do that, we get y minus x plus 1 times x plus 1 over y all over y squared. And from part D, we know that 1 comma negative 3 is a point on the graph, so we can plug that into the equation, and we get negative 3 minus 2 times negative 2/3 over 9. And when we simplify that, we get negative 5 over 27. And because this is less than 0, we can conclude that the estimate from part D is an overestimate because f of x is concave down at x equals 1. And just to show this graphically, the blue line represents the tangent line of the graph, and the red line is the actual graph of the equation. And you can see at 0.5, the blue graph is obviously higher than the red graph, so we can visually see that it's an overestimate.